Alrighty, so let's look at another problem. By the way, this is part 2 of the first of part 1 8.5 video that I released previously. And in this part, we're gonna discuss both things. Let's read this problem first, and then talk about what's gonna be in the video. Let R be the region enclosed by the graph this and a horizontal line of y equals 4, as shown in the figure above. There's no figure above, but there's this figure, so we're going to be talking about there's this figure. So find the volume of the solid generated when R is rotated about the horizontal line y equals -2. Now, there are two things that are new to you that wasn't covered in part 1. For one, we have two equations that are being enclosed. There's this equation. Let me get a different color. There's this equation and there's this equation, where in the previous problems you only have to worry about one equation. Also, it's not being rotated around the x or y axis. It's being rotated around y equals -2. Which brings us to the Washington method. I'm going to talk about the Washington method before I continue talking about this one. In the previous one, the disk method, you pretty much took, let's say, you took a parabola, you found its area, and then you pretty much turned it I'm looking for the word, rotated. You rotated around, let's say, the y-axis to create some kind of cone-like, but I think it's called the paraboloid or something, a cone-like figure. So that's the disk method, and the reason why they call it the disk method is because if I took this slice right here and I looked at it from the top, it would look like a disk. Now, there's something called the Washington method, because let's say this is not one function where you find the area. Let me go ahead and erase this because it suspiciously looks like an x-axis. Let's say you have two, and to keep it simple, let's say you have a parabola underneath a parabola. And then we talk about that area enclosed, you know what I mean? And then we rotated that, and then we looked at a slice. You would end up having a disk. And to find this disk, you pretty much find the area of the outside, which is pi r squared, and the area of the inside one, which is also pi r squared. Well, let's go ahead and write a big R, because it's a different R. You can tell that this radius is very different from this radius. And this will represent, when you subtract them, this will represent all of this area right here. You know? So that's how that's going to work. That's what we're going to be doing. We're not going to create disks anymore. We're going to be creating, if you have two functions, you're going to be creating washers. And you do that by having the outside area minus the inside area, and that will give you the area enclosed. Just like we did in the previous video, not the previous video, where you did like top minus bottom. Top function minus bottom function if it was dx, or right minus left if it was dy. Going back to this, that was fun. So we have these two functions, and if you look at the drawing, I'm guessing that this function right here is the x to the 4th minus 2.3x cubed plus 4. And we're going to be rotating it around y equals -2. Y being -2 is like down here. So we're going to be rotating it. So we're looking for this area right there. That's pretty much what we're doing. Boom. So let's talk about the radius. We have one radius right here. That's why my wife just called and I answered it. Alrighty, so back to what I was saying. So we have that small radius. I mean that the one that I talked about right here. So we have that small radius, this one, which for some reason I called big R. And then we have a big radius, which is going to be from the very top. And I like that one. That one I like the most because it stays the same. It's a horizontal line, so it's going to be Let's see, that's 4 minus 2, that's 6. This is 6. So no matter where you take the slice from, the washer will always have the outside radius of 6. So that's kind of nice. But the inside one is going to be a little different. We're going to have the inside radius is going to be whatever f is plus 2. Because the f function only tells you the distance from the, let me use a different color. The f function for this guy is only going to tell you distance from the function to the x-axis, you know? But since you're rotating it around y equals -2, you're going to have to add 2 to that to get that radius. So this is going to be f plus 2. F plus 2. So you have to consider that. So let's do this. Yeah, let's go ahead and do it. So dv, the little washer is going to be pi. Because dv, we're doing an integral, so we're adding a bunch of dv's to create a figure. So that's why dv is expressed right here. So the washer is going to be pi, big R, which is going to be 6, minus, and then the function plus 2, which I see they did. And now, of course, you're going to square those. And then dx, because we're drawing it the way I just drew. Whenever you do vertical lines, when you do slices, it's always going to be dx. If I was drawing slices like this, let's go ahead and use blue. If I was drawing slices like this, then I would have used dy. I digress. So this is going to become 36. When you plug that in, that's going to be a 4 plus 2, so plus 6, which is expressed right here. 36 minus, and then all this good stuff, plus 6. And then you do the integral. Pi can be pulled out. I use a calculator for wrong. Straight up stopped it. Do you need to use a calculator? I don't think you have to use a calculator. Can you? Dang it. You can do it. It's not that hard. You just have to foil, but a trinomial, and that stinks. You know, you're gonna get like 17 terms. Alrighty, so yeah, go ahead and use a calculator. So just plug this into your function, and do an integral from 0 to whenever they intersect, which apparently is 2.3, and you should get the volume of this figure as it's being rotated. So if I was to draw it, it will have like a hole, like all of this is going to be empty space. All of this is empty space, you know. It's going to look like almost like a wine glass, except the middle part is really thick. Alrighty, so yeah, that's it. That's that one. So that's the washer method. When you have two functions, you have a washer method. The fact that it wasn't rotated around the x or y axis is the reason why we had to worry about that plus 2 right there. So it's not overall a hard problem. Just integrating this one ended up being hard because when you square this bad boy, that's going to be a large thing to deal with. Let's move on. Alrighty, so let's look at this one. Let R be the region enclosed by this graph and horizontal line y equals 4. And the region blah blah. Region R is the base of a solid. For this solid, each cross section is perpendicular to the x-axis. X-axis is an isosceles right triangle with a leg in R. Find the one with the figure. Okay. Alrighty. In this case, you pretty much end up having all these triangles. It says it's perpendicular, so I'm guessing this is what they look like. One triangle, and then 2 triangles, and 3 triangles, blah, blah. So, let's do this. So the basic area for a triangle is 1/2 base times height. So finding each individual, maybe I shouldn't use a highlighter. By the way, this has really nothing to do with washer method. So, you know, I'm sorry for that. Oh, right triangle. I saw this right triangle. So boom. So this should be the same as this, and then we have this right there. So because it has to be right. Alrighty. So 1/2 base times height. Base and height should be the same because isosceles. And then, yeah. So the area would be that, and you add them all together by doing integration, you're going to end up creating this figure, which looks weird. You know? It's kind of... It's just a bunch of triangles added together to create this. And I want to emphasize, this has nothing to do with the washing method. We're just kind of doing this. It's in here for some reason, so we're just going to go ahead and finish it. As part of an AP question, that's the thing. Alright, so we have this being the same, and this right here would be, this is y equals 4. We have to subtract whatever this side is, so y equals 4 minus f, because this is going to be f. Here's the thing. Let me use different colors. Why do I have blue twice? This right here is 4, right? But we don't want 4. We want this. So what we got to do is we got to remove this. So this entire red piece is 4, but we only want what's in black. So we're gonna have to subtract what's in green. So that's why we have 4, but just the red stripe. This is 4, and in order to remove, let's go ahead and use blue now. This part we're gonna subtract f of x. So that's what this is gonna be, and because it's an isosceles triangle, this is gonna be the same thing. So I'm a 4 minus f of x, 4 minus f of x, and we have our little slice of a triangle. 1/2 base times side is the area of this triangle, and we have only one of them, which is why it's dA, not the entire. You keep adding all of them together. You add them all together, you're gonna end up getting your volume. So your little dV is going to be this, but you're gonna have your dx, because if you add some kind of thickness to it, this is just an area, but the moment you introduce a little thickness, then it becomes a volume. So here's the integration from 0 to 2.3, because that's when they intersect apparently. From 0 to 2.3, 1/2 times that squared dx. And then you do it, use a calculator again. I'm not going to spend too much time on that. And then it continues right here. Yeah, I'm not going to worry about that at all. I need to teach you guys about washer method. This is feeling like I'm getting off topic with what I'm trying to teach in this video. So this would be like an AP question they might ask you. This was a very hard paragraph to understand. You know what I mean? Oops. This was a very hard paragraph to really understand. You have to kind of look at keywords. Perpendicular to the x-axis is what kind of told me it's the triangles are happening this way. And then the fact that isosceles triangle kind of told me that the base and the height were going to be the same thing, which is going to be whatever this length is. So it is not an easy problem. So if you followed me, good job. Good job. All right, so let's move on. We're not going to worry about C. Hopefully the next one is the washer method. Alrighty, the last problem actually isn't the washer method one. It's kind of similar as the other one. You have to figure out the dA. So you figure out an area, then you introduce some thickness to make a dV, and then you do an integration. So I really have mixed feelings about doing this. So I will go ahead and do it, and I want you guys to watch it, but not take notes on it. And then I'm going to take a picture of another washer method problem, and then we're going to have you take notes on those. How about that? So just prepare to, for this video it's going to be a little longer. It's fine. Just skip ahead. If you, no, I don't want you skipping ahead. Watch this. Just grab some popcorn or something. Alrighty, so let's read this. So let f equals this and g equals that. R is the region bounded by the graph of f and g. Okay, that makes sense. That just tells you that this is going to be the bottom part of it. We don't know what kind of figures we're going to create, because we could be creating some triangles up in here. We could be creating some squares. It looks like it's going to be squares. We could be creating all kinds of stuff. And as we go to like the narrow ends, like the square would get smaller, you know what I mean? So that's pretty much what we have to worry about happening. So this is our R. This is just a base. Doesn't tell us about what the figure is going to look like yet. As shown in figure above, which is figure below. I don't know why they call above below these days. Or below above. The region R is the base of a solid. For this solid, each cross section is a perpendicular to the x-axis. Okay, so it's got perpendicular. So it's going to be rising, you know. It's going to be like that. It's not going to be like this, because that would seem parallel. Like the square isn't going to be like this, like facing. It's going to be. I'm really bad at drawing stuff, but let me see if I can do this. What that means is, if I'm actually going to add some, this is what the solid is going to look like. Once I add like some, and then, actually, this is what each square is going to look like. Alrighty, because it's perpendicular. Alright, that was actually a really good job. That was pretty good. I was doubting myself. Alrighty, let's continue. We have so what was it? The square, right? Do not evaluate the integral expression that gives the volume of the. Oh, nice! You don't have to like do it. That's ideal. So the average square is going to be s squared, and s is going to be this distance right here. So it's going to be whatever this is. So we have to pretty much do the top function minus the bottom function, and yeah, just have to do that. So the top function seems to be, what is this? How do I know which one's the top function? Alrighty, this is clearly the cosine function. Clearly. I know what cosine looks like. So the top function is cosine, so it's going to be cosine minus, yeah, there we go. It's going to be cosine minus the other function, because the bottom function seems like the other one. So that's just the area. When you introduce some thickness to it by adding a dx to it, so without dx, dA, there's no dx, see? You attach a dx to that, dv, because you're taking an area, you're multiplying by thickness. Thickness, this is dx right there. This is dx. You're adding some thickness to it. And then we integrate it from 0 to 2, because that's where they intersect. Alright, so boom, and this is fine for the AP test because it says write but do not evaluate. Nice. So that's all we have to do. Alrighty, I want to finish this video by having one more a washer method. So here it is. I copied it from the book. The region between x equals 0 and x equals 8, okay, and bounded by the graphs blah 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 blah, is rotated around the x-axis to form a solid. Find its exact volume. In this case, you don't have to worry about where these guys intersect, you know, because they pretty much tell what the bound is. You do need to know what they look like. So we take our little graphing calculator out, boom, and we put our functions in there. Clear window. We need to go from 0 to 8. So 0 to 8. And as far as y goes, I'm going to expect this to be above the y-axis. So it's going to be way bigger than 10, I think. I think we're going to be dealing with big numbers. Because, I don't know. No, it could be either way. I don't know. So I'm just going to go ahead and try that out. First function is x raised to the, and then 1/3. How do you do 1/3? 0.33333. That's good enough. And the other one is going to be x 10 times exponent. Where's my exponent button? Boom. And that exponent is negative 0.1 times x. Okay, so let's graph these two. That's the first one, and that's the second one. So the second one was so the top function is going to be the 10 times e to the negative 1.1x. Okay, so we have our graph. That's what it looks like. That is what it looks like. So I'm gonna. Is there any way I can take a screenshot of that? Okay, boom. There we go. We got that screenshot. So let's do this math. Alright, so we are pretty much dealing with the top function minus the bottom function, you know, because we're doing this. Oh, wait, are we doing this around the x-axis? Yeah, around the x-axis. In order to get this radius, in order to get this. So let's do it first. Let's go ahead and write down pi r squared, which is top function, 10 minus e to the negative 0.1x. Come on. And then that's being squared minus, and then we're gonna, I don't want to have to write pi twice, minus, and then x to the 1/3. And then we're gonna do dx. Alright, that would be a disk. Yeah, that would be my disk. Just making sure I'm doing this right. I'm introducing some thickness. So that's dx right there. Perfect. Yeah, that's how you do it. So we have this little this little disk, and then we have this little thickness, which is dx, and we're gonna keep adding them across. So we're gonna have an integral. That's I have a tool right there that's kind of in my way. Whee! When we do that from 0 to 8. Yeah, that's it. And then we're gonna use our calculator to do this. So we're gonna need another video. Alrighty, so let's do this. I actually already plugged it in, but let me just talk about what I've plugged in. I ended up getting 2,119. I went to math. When you go to math, there's a option right there. Oh, oops, sorry. When you go to, so there's a math button right there. I press that, and then there's a integrate section right there. You press this, and then it pops up a brand new integral that you get to make. And I kind of just messed some up, so I'm gonna delete all this. Delete. How did I delete this? Delete. Go away. So it brings up an integral, which I already plugged in. I plugged in everything exactly the way we had before. Just to make sure I did it right, I had to deal with a lot of parentheses. But I did my integral from 0 to 8, like it said. Then I took a pi out on the very outside. So starting a parenthesis. By the way, this parenthesis was default. I didn't put that first parenthesis in. So inside my big parenthesis, I have my first radius, which is the very top function. Squared it, and then I did my other radius, and I squared that one as well. And then I inserted a parenthesis, and this parenthesis came with the entire thing, and I made it dx because the thickness has to do with dx. And when I pressed enter, I just accidentally deleted the x, but there was an x right there. Fun. And when you calculate it, I'm not going to do it again because it took a long time for it to calculate, I got some like 2,119. And that's it. That's the end of the video. See you guys tomorrow.